All right, guys, we are going to look at polyprotic acids. Up to this point, we've looked at monoprotic acids. With polyprotic acids, remember, poly means that there are many. Protic refers to protons. So polyprotic acids, there are multiple protons that get released or exchanged. So our protons here are dealing with our hydrogens. So these are going to be acids that have more than one hydrogen that can ionize. So these typically, when we have the formulas, they will have, sorry, my pages are out of order. There will be like 2 or 3 hydrogens at the beginning of the formula if it is a polyprotic acid. So with these, whenever they ionize, they do ionize in a series of steps. So even though it may have 2 hydrogens that can ionize, it does not lose both hydrogens at the same time. It will only lose 1 proton or 1 hydrogen at a time. So this is going to be a multi-step process. So for example, here is sulfurous acid that has 2 hydrogens. It will ionize losing 1 hydrogen, producing a hydrogen sulfate ion. And then that hydrogen sulfate can ionize losing a second hydrogen to produce the sulfite ion. So instead of losing 2 hydrogens at a time, it lost 1 hydrogen at a time, and that product that still has a hydrogen that can ionize went through another step overall. So this would be a 2 reaction process. And like I said, the first one with the sulfurous acid, whenever it's in water, produce those hydrogen ions, the hydroniums, and the hydrogen sulfate ion. Then the hydrogen sulfate further reacts with water to produce more hydrogens and the sulfate ion. So anytime we have polyprotic acids, you are going to see these in multiple steps. And for each of these steps, they have a Ka value. So there is a different K value for each individual step in the process. So for the first step with this one, it has a Ka value of 1.4 times 10 to the negative second. And then the Ka value for the second reaction with the hydrogen sulfate ion is 6.3 times 10 to the negative 8th. So I want you to notice that the first Ka is relatively strong in comparison to the second Ka. So the Ka for the first reaction is always going to be much larger than the Ka for the second reaction and the third reaction if a third one is necessary. So to show you how this works in terms of an ice table, because these are still going to be weak acids for majority of them. So we said here we have the sulfurous acid producing the hydrogen sulfate. Say we started with 0.5 molar acid and none of the original ions. Our reactant would decrease by a factor of X. Our products would increase by a factor of X, giving us equilibrium values that we can plug into Ka. So wherever we plug that into Ka, we get the products are X squared over the reactant of 0.5 times or minus X. X cannot be ignored there because there's not at least 3 decimal points different. So if this were to solve for X, we would end up with X is 0.077, and that could be plugged in to our ice tables. Well, then our product ions also show up in the second reaction. So the second reaction had the hydrogen sulfate ion and the hydrogen ions along with the sulfate ions. So for our second step, the hydrogen sulfate and, oops, sorry, it is not aligning. Our hydrogen sulfate and our hydrogen ions are already present initially, and we have none of the sulfate to begin with. Sorry, I don't know why it's not aligning. And then it can still subtract by X on the reactant side, increase by X on the product side. And whenever that plugs into the Ka equation for the second one, we would get that X for the second reaction is much smaller. Now, where this comes into play is whenever, sorry, these are not aligning. So like we said, with polyprotic acids, the Ka for the first reaction is always much larger than any subsequent or later Ka reaction for the second reaction or the third. And because of this, the pH of that acid can be determined from the first ionization. So the X value based off of the Ka for the first reaction. And the reason behind this, if you go back to that example, the second reaction, the X value is so small that in terms of sig figs, it ends up not changing our concentration of our hydrogen. So we had our concentration of hydrogen from the first reaction was 0.077, and we said our X value for the second one was 0.6 times 10 to the negative 8. If you were to put in your calculator the 0.077 minus 6.8 times 10, I think it was 6.8 times 10 to the negative 8, your concentration is still 0.077 whenever you round it. So because those subsequent K values are so small and the X values are so small, they end up not changing the pH for that particular substance. So let's look at a problem with this. Here it wants us to find the pH of a 0.078 molar solution of phosphoric acid. And phosphoric acid, we would set up our equation whenever it is in water. It makes the hydrogen phosphate ion and hydronium. So this is that first reaction. We would record our concentrations, and we would expect the reactant to decrease by a factor of X. Our products would increase by a factor of X. Those we could plug into the K equation. So Ka for the phosphoric acid is 7.52 times 10 to the negative third. I don't know why that just went on a second line. So that would be equivalent to X squared over 0.078 minus X. Here we cannot ignore X. So when you multiply and you have to rearrange a little bit, we would get that X, I don't know if you can read that, we get that X is equal to 0.021 molar. So that would be our concentration of our hydronium ion. And whenever we do the negative log of that, we're going to get that it's a pH equal to 1.68. We do not have to do the second and third reaction for this one because that X value will end up being so small that it will not change that overall concentration. All right, this is one we're going to do something very similar in class. But this one wants you to find the concentration of all species present in 0.1 molar carbonic acid. This is one of the more difficult problems with this because it wants the concentration of every ion in every step. So you would have to do an ice table for the first reaction where the carbonic acid is producing hydrogen ions and the hydrogen carbonate ion. You would have to get those equilibrium values, and then you would in turn have to take the hydrogen ion and the hydrogen carbonate ion, mix them with water, and then the hydrogen carbonate can produce carbonate. So that's where you would have to use the product values from the first one as your initial values for the second reaction, similar to the problem we had earlier. If you want to try this on your own, here are the answers you should get. And you'll notice that that hydrogen ion concentration should not change very much from the first reaction to the second reaction. Ka values can be found in your textbook. So this is one that I may practice, but like I said, we're going to do one like this together in class, but it is still using the ice tables. But you're looking for the equilibrium amounts for every different ion that exists between both reactions. Let's look at one more. Here we want to find the pH of a 0.50 molar solution of sulfuric acid. And it is a polyprotic acid. Sulfuric acid is one of our stronger ones. So that means that it would ionize completely for that first hydrogen. So our first reaction is where the sulfuric acid, sorry, that was not aligned. The sulfuric acid mixes with water to produce the hydrogen sulfate and the hydronium ions. Like I said, since sulfuric acid is one of our strong acids, that means it will completely ionize. So our concentrations of our ions would both end up being 0.50 because that completely ionizes. If we were to look at the secondary reaction of the hydrogen sulfate with water, producing the sulfate ion and the hydronium ions, we would start off with our equilibrium amounts from the first reaction. So sulfate would end up being 0 initially, but the others would have an initial concentration. Our products would increase and our reactants would decrease, giving us our equilibrium amounts. If we look at the Ka for the second reaction, it's going to be 1.2 times 10 to the negative second. We plug in our products over our reactants, and we cannot ignore X here at all. So you are going to have to do a little bit of algebra and simplifying. Here we get that X would be equal to 0.011. If that plugged in to our ice table, we get that equilibrium concentration is going to be 0.051. So it did not change much from the first one to the second one. So our pH would end up being 0.29. And like I said, typically your pH is going to be between 0 and 14. If it ends up being negative, that is possible. But that's an instance where it's not going to change the pH much from the first reaction to the second. If we had just plugged in the 0.50, our pH would be 0.30, so it's 1/100th of a difference. So that would not really matter. We're going to do some more examples with these in class. That way you can get practice with them. But remember, overall with polyprotic acids, it is only ionizing one hydrogen at a time. And typically you're going to be able to find the pH based off of that first ionization and not have to do every single reaction.